Recording in progress.
Okay, I think it's time to start. So I'm happy to open a second session of our seminar. And in this session, we are going to learn a lot about different quantum simulator and hopefully quantum computers. And I'm happy to introduce the first speaker in our session, Misha Lukin, who doesn't need any introduction. And I'm sure that we are going to learn about really new frontiers in quantum science. Thank you, Misha.
Thank you, Ola. So I'd like to thank the organizers, and in particular Ola, for invitation and for maintaining this this meeting and this tradition. So indeed, I will be talking about building quantum machines, quantum simulators, and quantum computers. And I will focus on using neutral atoms as a basis to do that. And I would just like to kind of start my talk with how we typically start the experiments in this field. So we start typically the experiments with the cold atomic cloud using something which is called magneto-optical trap. It's a kind of workhorse of all cold atom experiments. And, when we do it, we typically, in each of these cloud, we have 10 million atoms. So basically 10 million atoms, if controlled individually, will become like, 10 million qubits. So what it really means is that there is basically, we have essentially unlimited source of cold neutral atom qubits. The key challenge, however, is to learn how to control them efficiently and control them, basically at a level of single atom. So motivated by this observation in my talk and in actually a couple of other talks in the session. So what we will be doing is we will be actually building these quantum systems literally atom by atom. And we will do it by using the tool which is called optical tweezer. So it's a basically tightly focused laser beam where each of this focused laser beam can actually attract kind of dielectric objects to the point of highest intensity. And so atoms are kind of a dielectric objects, and we will focus these beams so tightly that each of the tweezer can host at most one atom. So the two atoms cannot fit inside, they would be ejected. So what we'll do to build our systems is we will start not just with one tweezer, but as you will see in a second, with thousands of tweezers, and then we'll try to load all of them with atoms. And of course, what will happen is that the system will have some entropy. So some tweezers will be loaded and some will not. And we will get rid of this entropy by literally taking a picture of this atomic array, figuring out which of these tweezers are full and which are empty, and then basically kind of eliminating the empty tweezers and then rearranging the rest of the atoms in a kind of desired configuration. So that way we'll end up with basically an artificial kind of system composed of atoms positioned essentially at will. So the atoms, after this kind of rearrangement, will be separated by a couple of micrometers. As such, they will be completely non-interacting. So to induce interactions, what we'll do is we'll actually excite these atoms in a Rydberg states. So that way we will induce either strong interactions, or we can do things like quantum logic operations and things like this. And so this is actually a project that we started together with some other speakers in the sessions, which will follow my talk, but also with my colleagues at Harvard, Vladimir Vuletic at MIT, and at Harvard, Marcus Grein. So let me just talk a little bit about Rydberg atoms. So we like Rydberg atoms for two reasons. One is that Rydberg states have relatively long lifetimes, typically hundreds of microseconds, and they have also strong interactions. So in particular, van der Waal interactions between two Rydberg atoms, for example, excited in the state with n equals 100 are 14 times strong, 10 to the 14 orders of magnitude times stronger than the interaction, than the van der Waal interaction between the ground state atoms. So 14 orders of magnitude is a large number, and we can make good use of that. And so one way how we use them is this idea of Rydberg blockade. So, and the idea is the following. Suppose we just start driving atoms into Rydberg states resonantly. And so if the atoms are sitting very far away, they will just undergo independent Rabi oscillations. But if the atoms come closer, eventually these interactions between Rydberg atoms will take over. And if you still try to excite the atoms resonantly, you will not be able to excite both atoms simultaneously. You will be able to excite one atom or another, but not both simultaneously. So what it really means is that the simultaneous excitation will be blocked at distances smaller than this characteristic blockade radius. And it turns out to be a very good mechanism, very robust mechanism to entangle atoms and do quantum logic, because it's insensitive to motion and position of the atoms. So in short, and what follows, what we will be doing is we will assemble some system from single atoms, positioning them at will, and then shine sequences of laser pulses, changing their hyperfine states, sometimes exciting them into Rydberg states. And then eventually we'll take a picture of the atoms again in a state-dependent way. So this will be a projective readout. And so it turns out to be kind of a very powerful platform for all sorts of things, for quantum metrology, for quantum simulations, for quantum computing. So it's actually now there are several hundred experiments of this kind that are being built around the world, and actually at least 6 companies who are trying to commercialize this technology. So starting from about kind of early 2020, in our lab, we ran what we call second generation of atom array. So in this second generation, we started from about 600 traps, and we were able to basically sort and create kind of systems of about 300, a little bit more than 300 atoms. So what you see here is basically kind of artificial lattices, square lattice, triangular, hexagonal, Kagame, the kinds of systems we were able to create, and we also experimented with the system. So we can also, for example, start with arbitrary patterns. So for example, this is a pattern that you would like to create, and then you press a button, and here is the atomic structure which emerges. And so, as I said already, we started with about 600 traps and ended with about 300 sorted atoms. So basically, each trap is, sorted, is filled in this case with about 99.5% probability. And so, using the system, we could kind of immediately explore several directions. So one of the avenues which we have, played with a lot is to use it to, for example, to explore quantum phase transitions. And this idea is actually very simple. So suppose you start with the atom array, for example, in the square lattice, and each atom in this case is effectively a two-state system with the ground state and the Rydberg state connected with the coherent laser driving. So, and you can describe the system with this simple Hamiltonian. So this is a laser driving, this is a detuning term. It's actually acts as a chemical potential in some way. So N is a number of Rydberg atoms on each lattice side, 0, 1. And the final term is the interaction term, and it describes this Rydberg blockade. So suppose, for example, we adjust Rydberg blockade such that basically only nearest neighbor is blocked. And then what we can do is we can basically play with this detuning term to actually study transitions between different, states, between different phases of matter. And so, for example, if delta is negative here, then it turns out that basically, you would like to have n equals 0 on each lattice side. So it means that the ground state of the Hamiltonian should be all atoms in a grounds, all atoms in a kind of lower state, ground state. And if we now take this detuning and basically change it from negative to positive, then once in a while, what we'll see is this kind of order emerging. And this kind of order is basically every other atom is excited. So it's, in antiferromagnetic state. So admittedly, if we repeated the experiment many times, not on every shot we see a picture like this. So often we see some kind of domain walls, and so we have to study this. We have to evaluate things like correlation functions. And actually, indeed, if you look at correlation function, that you see is that we basically see order, antiferromagnetic order, extending across the entire array. You can also study this kind of images microscopically. And so what happens is that this type of kind of ordering, perfect ordering, is both not very frequent for large system size, is still the most probable. So basically it turns out that this kind of order and the order where the lattice is shifted by just by one lattice side are two most probable. Moreover, you can also study dynamics of this phase transition. So, for example, what you can do, you can go across this, you can change the tuning at various speed. And what you see is that basically here is if you change this, slow, then you see this perfect order emergence. If you kind of change it quickly, then, this correlation length actually does not grow very much. But actually, it turns out that you can use this kind of information to understand the nature of the phase transition. For example, by rescaling these curves with the speed with which you evolve, you can basically extract things like critical exponents. And in fact, it turns out that what we have done here is it corresponds to the first observation of this so-called 2+1 quantum Ising phase transition. So it's actually, textbook phase transition, which has not been seen up to now. And so with kind of a system like this, we actually had a lot of fun over 2.5 years or so, and we studied all sorts of exotic phases by playing, for example, with lattice geometry and with adjusting Rydberg blockade mechanism. So we also studied non-equilibrium phenomena by pushing actually system far away from equilibrium. We actually made a kind of a small discovery. Now it's a phenomenon which is called quantum many-body scars. We also kind of studied topological physics, realizing something which is called quantum spin liquid, which actually was for the first time proposed 50 years ago, but have not been seen in the lab until now. So I'll talk a little bit about these two topics here, about accelerating combinatorial optimization and also about kind of building a general purpose quantum computer and quantum error correction frontier in my next 20 minutes or so. I should say also that, we now have more than one machine of the type that I am describing in town. And actually, so across the street, our colleague and our colleagues in our startup company, Quera Computing, have actually built a, very similar machine to what I described. And it's actually now publicly available through AWS cloud since last November. And actually, there are already quite a few papers have been published using this system. Okay, so in what follows, I'll just give two quick examples, of what kind of things which one could do with that. And so the first example will be this example of trying to accelerate a solution of combinatorial optimization problem. So, and one specific problem that I will focus on is something which is called maximum independence set. So it's a simple mathematical problem in which you're given a graph. The graph has some vertices which are connected by edges. And basically what you would like to do is you would like to color as many vertices as possible, but you cannot color two vertices which are connected by the edge. So that's what's called, that's called independent set. And so basically the goal of this problem is to find the maximum number of vertices that you can color, without violating this independent set constraint. So what is shown here is a specific example of this problem, which is called maximum independent set on a unit disk graph. So basically here, vertices, all vertices are connected, which are within certain distance from each other. So this problem is kind of interesting from different points of view. So first off, it actually has many real-world applications like design of logistics, of networks, machine learning, and so on. So it's actually the problem to solve it exactly. It's actually NP hard. It's known to be a very hard problem to solve. But moreover, if you followed my talk up to now, you will realize that this problem has very intrinsic connection to the Rydberg blockade. So in particular, the cost function of this problem is basically corresponds to the classical part of the Rydberg Hamiltonian problem. Remember, in this Rydberg blockade Hamiltonian problem, you would like to excite as many atoms as possible, but you cannot excite the atoms which are within this within this Rydberg blockade constraint. So basically, it turns out that this problem here is kind of identical to that. And so, what this kind of allows us to do is allows us to very efficiently encode this maximum independent set in our Rydberg machine, and try to explore, this kind of quantum optimization in a hardware efficient way. And so basically the idea here is that, by encoding it, we will be able to, for example, go explore it at kind of what's called large circuit depth, and with much larger number of qubits than kind of otherwise possible. So here is how we do it. So we basically associate each vertex with a single atom on this atom array, and we define the connectivity by just defining a Rydberg blockade radius. And so after that, what we do is very similar to what I described already so far. We start with all atoms in the ground state, and then we design some pulses to excite the atoms simultaneously with radio frequency energy tuning, with the idea to basically maximize the number of excited Rydberg atoms subject to this Rydberg constraint. And of course, we have a choice of how to design this pulse, and we can pick the algorithm. And so in this talk, I will focus on what we call a variational adiabatic algorithm. So basically what we'll do is we'll just try to change this detuning in time in some way, and do it kind of in a way to kind of maximize the number of Rydberg atoms. So it's actually will be done in practice using this closed loop optimization scheme. So one, of course, has to kind of pick the target. So you can either ask what's a sort of one can ask figure, basically what should be a figure of merit that you want to optimize. It could be either approximation ratio or MIS probability. And actually with these tools, with the kind of supported by DARPA ONIS program, we actually have, basically explored a wide variety of graphs. So basically what we have done is we then just picked, thousands of graphs and kind of threw it in our kind of at this machine, and just try to see how well this kind of machine work. And actually it kind of is very interesting, because the graphs which are sometimes which are very similar size, if you just change them by a little bit, you see that the difficulty of optimization changes by orders of magnitude. So I would like to just focus on one aspect of this, and actually this is benchmarking this optimization against simulated annealing. And simulated annealing is a kind of well-established classical, general-purpose classical algorithm, in which essentially what you do, you take this kind of system like a spin system, and you basically try to cool it by stochastically flipping spins. So there are many versions of the simulated annealing. In fact, to make a fair comparison, we try to optimize the simulated annealing, and in this case, we used something which is called collective updates. And then what we can do, we can just take the graphs and give it to a quantum machine or give it to a classical machine and compare how they perform. So this is kind of an error plotted 1 minus approximation ratio. four different graphs, different colors correspond to different graphs as a function of depth, how long you run this algorithm. And there are clearly two regimes here. One is a high energy regime, where we basically get, all these curves, kind of more or less proportional to each other. But there is this kind of low energy regime. And here clearly something interesting happens. So for some of these graphs, you see, they kind of approach a good approximation ratio, but then they get stuck classically and they remain stuck for a long time. And basically quantum machine for that, it really can solve these graphs quite a bit faster. So what's going on? So what are these special graphs? So these special graphs are the graphs which are actually hard for simulated annealing. So these are the graphs which have a lot of approximately good solutions. So basically the solutions where, the cost function is almost optimal, but not quite. But for that, they have very few actual solutions. So, and what happens is that the classical algorithm basically ends up doing kind of a random work on this hypergraph, kind of gets stuck in this kind of approximate local minima, and really has hard time kind of finding the actual solution. And so once one understands it, one can actually show that in fact there is something which is called hardness parameter, which is basically a number of these solutions with MIS -1 divided by number of edges leading to the good solution. And it turns out that this hardness parameter actually scales exponentially with the system size. So that's actually a signature. It's an indication why this problem is NP hard. And so what we do next is we just focus on these hardest graphs and pick 2% hardest graphs for each system size, and then compare again classical and quantum. And what we find is there are different instances behave differently. So classically, by definition, these graphs are hard, so it takes a long time for classical algorithm to find it. But quantum mechanically, in some cases, quantum system just solves this problem. In some other cases, it actually kind of gets stuck. And so again, what we do is we now throw a lot of these instances and compare. And what we find is that for many cases, quantum machine performs. That's a performance plotted basically at a certain depth. Quantum machine performs better than classical, but not on all instances. In some cases, actually, quantum machine is actually worse than classical. So what's going on, and in particular, what is actually controls the quantum hardness? So it's actually not surprisingly, it turns out that quantum hardness is controlled by a minimum energy gap. So the way how we know it is we basically find that for the cases where we can calculate where the minimum energy gap occurs, we find that our optimized quantum algorithm actually slows down at this point of minimum gap to actually find the best solution. And what we can also do is we can basically plot this probability to find the MIS as a function of the gap. And what we see is very nice Landau-Zinner scaling, which basically indicates that indeed the smallest gap is what controls the quantum hardness. And we actually also see here that there are two regimes. One is where there is very nice matching to the Landau-Zinner, and there is one where there is no matching at all. And actually, we understand it because this is the regime where we can actually where our evolution is not long enough to resolve this minimum gap. And so with this knowledge, we can analyze our data differently. So basically, we can, for example, focus only on these points where we can resolve the minimum gap. And what we see is that for those instances, we basically see superlinear, nearly quadratic speed up in this kind of deep circuit regime. And actually, in fact, this was our experimental observation we published about a year ago. And actually, we now have a lot more understanding. So we actually now were able to prove theoretically that there is that it's possible to have a quadratic speed up for a certain class of these for hard instances of unit disk graphs. So we are also exploring the ideas for faster than quadratic speedup using this kind of overlap gap property as a concept in computer science. And we're also looking for scaling up, in particular, looking beyond unit disk graphs, controlling and mitigating errors. So let me now switch gears a little bit and talk just a little bit, about this kind of other direction which we are pursuing, and that's related to building a larger systems and more programmable and using this idea of quantum error correction. And to do that, what we will do is we actually switch the types of qubits we will be using. So far I encoded qubits in ground and Rydberg state. So at this point, I would like to rather encode qubits in the superposition of the two hyperfine states. And we knew from very early days, that it's actually a better encoding in principle, but up to very recently, it has been actually challenging to get, very high fidelity manipulation of these qubits, in particular, to entangle qubits stored in the states with the high fidelity. And actually, this has started to change already about 4 years ago, thanks to the advent of what we now call Levin-Pichler gate. So basically, and the essential idea is the following. So if you would like to manipulate quantum information in the states 0 and 1, you actually, what you need to do, for example, some entangling gate. And what it means is you need to basically imprint a pi phase shift, for example, for qubits stored in states 1, 1. So it should be a conditional gate. And what Harry and Hannes were able to do, they were able to find a very clever pulse scheme which contains 2 pulses, which basically just imprint this, this phase in a kind of very fast and robust way. And actually, we implemented, like literally the next day after they came up with this idea, we implemented this scheme in our experiments, and it worked quite well. And actually, it worked with the kind of gate error of about 2.5%. And so immediately with this kind of realization, we started kind of experimenting with what we can do with them. And the key idea here is that if qubits are stored in this hyperfine manifold, not only the storage time can be very long, but also we can move atoms around while preserving coherence. And so specifically, this is an example. So suppose we started with pairs of atoms like this, and we can basically entangle them by using this controlled phase gate, and then we can either measure them directly here when they are in this place, or we can move them around and basically check if entanglement is preserved if we move them far away. And in fact, it's perfectly preserved. So this gives rise to this kind of idea of this reconfigurable architecture where we basically start with atoms located in some way, perform some gate operations, and then, change the atoms, change the connectivity basically dynamically, while doing a computation process. So, so basically it turns out to be a very powerful approach. So we already kind of did many experiments. So let me just so I'm running out of time, I apologize. So one of the things we have done is, related to basically implementing quantum error correction. So what is quantum error correction is kind of the idea basically to use redundancy to encode, to improve protection. Of course, in quantum mechanics, you have no cloning theorem. You cannot duplicate the information. So instead, what you do, you basically take the physical qubit and delocalize it, use entanglement to store the information non-locally. And so one textbook example of that is something which is called toric code, where you start basically with the grid of physical qubits, these black dots, and you use them to encode illogical qubits, which are building blocks for fault-tolerant quantum information processing. And to check for errors, you use this ancillas, use red qubits, which locally measure something which is called stabilizers. And so we would like to implement this error correcting code on a torus, because here actually topology helps to protect the quantum information. It seems hard, but actually using this movable architecture, it turns out that it's actually relatively easy to do it. So the way how to do it, you have to basically unfold this graph, like in a way shown here. And basically what we need to do just to create some non-local connectivity between these edges. And actually the way how to do it is to use, to move certain atoms, to take certain atoms and move them around. So, and in this case, in particular, what we do, we use actually 8 uncial atoms in an array, which we move around. So the red circle is actually controlled phase operation. And then what you see here, we move them all the way across before then just reading these ancilla qubits to correct for error. So using this approach, we can actually encode 2 logical qubits. And one of them is encoded, going one way across the torus, another one, another. And you can see we already can basically, correct some, correct some errors. So I think this actually is a very exciting kind of avenue. And I think I used up my time already. So we're now kind of running generation 3 atom array and already have some first exciting results. So these are the kinds of arrays we are working with. We actually now have, we can trap over 1,000 atoms, can sort, 500-600 atoms. And one big thing which we worked on early on this year is to improve fidelities. And I already mentioned that, fidelities have been kind of a challenge for this platform in particular. Even with this 2.5% per atom, it's sort of fidelities are not good enough. For example, to make quantum error correction useful, you need to increase fidelities to more than 99%. And actually, we have done this. We have actually improved these fidelities, and the way how it was done by combining new gate ideas, for example, ideas involving dark state physics, and also some technical improvements using stronger lasers and colder traps. So, and the way how we actually see that we improve these fidelities, we do something which is called randomized benchmarking. And what you see that, basically the errors here improved by more than factor of 5 to the point of 99.5%. And basically, we now actually developed, using these techniques, methods, we developed a full family of gate pulses, which actually can realize this high fidelity. And what's actually interesting is that we can immediately scale it. So we can do these experiments with many qubit pairs in parallel, and actually all these pairs, display this very good fidelity. To just kind of give you a little bit of the sense. So here is what we see in a lab. So here we prepare, in this case, I think some 90 Bell states, kind of in parallel. And, in one case, we prepare 0, 1 plus 1, 0. And actually, when we image the atoms, we only see one state. So you see here only single atoms appear. And so in this case here, we prepare 0, 0 plus 1. So here atoms appear in pairs. And so, okay, I think I used up my time already. I hope I convinced you that this is, a very exciting time, and there are some very special kind of opportunities. So I'd like to thank you for your attention and thank all the people, who contributed to this work. Thank you.
Thank you so much, Misha. Really exciting talk, and so many news. Like for 10 talks would be more than enough. And my impression in general that you are moving from simulation now to more to kind of computing, right? And it depends now how many atoms you can independently control completely, right?
Yeah. Yes. Yeah. So as a part, yes, that's right. So it turns out that computing and simulations are not very different. Mm-hmm. And for example, part of a generation 3 upgrade, we can now independently control all atoms. So we have a way to, by using acousto-optic deflectors, we can now control basically any atom individually in the array.
Mm-hmm.
Yeah.
I see. Great.
And that's it.
And maybe Vitaly, but only if short question.
I have a very general question. Do you have in mind to demonstrate in near-term quantum supremacy of your system, for example, using one of the standard condensed matter model, Hamiltonian, and which allow to compute the number p hat for classical computing quantity, and then you can somehow simulate this quantity on your computer.
Yes.
But the main question is, your Hamiltonian will be only approximately equal to the model. Is it still allowed to show quantum supremacy in your system? What do you think?
Yes, so we actually, yes, that's a very good question. So we can like ask the supremacy, but it's not a short question to answer. So there are ways to kind of demonstrate. So there is kind of quantum supremacy, which you can think of from the point of view of computer science kind of perspective. And there is one which is more like a kind of practical supremacy. So, for example, if we do quenches on these systems of like 300 atoms, there is certainly you cannot simulate quantum dynamics, classically. And so we have done experiments like this, and we actually made some discoveries. So, for example, this kind of what I mentioned, quantum many-body scar, is actually something we discovered in a lab. Of course, once you know the answer, often you can go back and come up with some approximate algorithm which would simulate it, but it's actually is a little bit defies the purpose. So because, kind of if you don't know the answer, you do not know, what kind of approximation to use. So, that's one example. So, but we're also thinking about things like, for example, sampling, which are more, kind of have more of the kind of computer science foundation. We're also exploring that. But I would say in terms of practical supremacy, we already have done experiments which you would not be able to kind of get the results which we obtained by classically, at least by brute force calculation.
Okay, we have to stop the discussion because we have to proceed, unfortunately. And so thank you so much again, Misha.
Yeah.
And the next talk in our session will be given by Hannes Bernian from University of Chicago. Could you share your slides?
Yes. How does this look?
Thank you. That's fine. That looks fine.
Okay, great. Okay. Thank you very much, Olga, for the opportunity to be here. And thank you all the organizers. I'm really excited to share our research here. And yeah, it's actually really great to go after Misha, so I can skip my complete introduction and I don't have to convince you that single atoms and tweezers are a really exciting platform to now build these large quantum systems that indeed could be simulators or processors. Instead, I will actually spend my time in the introduction to convince you why it might be nice to have this two-color scheme that you see here in the back. So what we do a little differently is that we don't only trap a single species of atoms, for instance, rubidium. Actually, here the blue dots here in the background are single rubidium atoms, but why it might be useful to trap two. And here we also trap single cesium atoms in yellow. So why would it make sense to have two different types of species? And actually, we can answer this question by looking at other quantum architectures that also use two different qubit types. For example, superconducting qubits, if you think about the Sycamore chip of IBM, you think about 54 computational qubits, but actually there are more qubits. There are also qubits that can be used as couplers to mediate gates between the qubits. Another architecture, NV centers, that I actually enjoy very much. There you also have two different qubit types. You have spin qubits and also nuclear spin qubits, where you could use the nuclear spins as your quantum memory, very similarly in quantum dots. And something that is maybe a little closer to single atoms would be single ions and trapped ions. People also use dual species approaches, for example, to realize sympathetic cooling between the two species. So what could it give for us in neutral atoms? Well, first of all, what you gain is when you have two species is basically you get a very easy independent control of the two species. They have very different transition frequencies, very different qubit frequencies, and even with global laser beams, you can now independently control them without any crosstalks. You can measure them, as I will show you, without causing any additional decoherence on the other species. And we have ways to reload maybe one species while keeping them to overcome atom loss. And I will also show you new types of interactions that you can realize when you excite these two species into a Rydberg state. So that's our starting point. That is our motivation. So in my talk, I will just briefly show you how we do this. And I will show you a first application where we take use of the fact that we can independently read out one qubit without affecting the other. We actually did a little error mitigation protocol where we use that readout information to correct for phase errors on the other species. And then I'm going to show you what happens when you excite the two species to Rydberg states, and it's slightly different from single species experiments. Then if there's still time, I'm going to take a broader view on how we might be able to scale these atomic arrays by basically coupling distant arrays with photons. Okay, let's start here. And actually, our setup is very similar to the setup from Misha's talk. We also use spatial light modulators to make these traps for single atoms. We use acousto-optic deflectors to move the atoms. But in our case, everything is to some extent 2 times. So we have 2 spatial light modulators at different wavelengths to have traps for rubidium and traps for cesium. And then sometimes we get away with just having one device. Actually, our acousto-optic deflector can sort both types of atoms. In reality, this looks like this. In these experiments, microscope objectives always play a large role. We use these to trap the single atoms. Our atoms start here at the top. We push them down, and then we cool them there, use these microscope objectives to trap and image the atoms. So what does this look like? Well, I've already shown you in my title slide. We have now these dual species arrays. They could be in a regular pattern, or we could, because we have 2 spatial light modulators, put them independently of each other where we want them. We also can make inspiring pictures, maybe of Chicago landmarks, and with that have a lot of fun. But of course, these are just pretty pictures so far. So let me actually show you one first small application where we use this independent control and readout. So this is what in the literature was proposed theoretically by Ken Brown's group, also Mike Bierchop's group and Howard Weissman groups. And it's basically the idea that if you have a quantum simulator or quantum processor that is subject to some global noise, so noise with long correlation length, maybe you could set aside some of your qubits to monitor this noise in real time and then actually perform a feedback or actually feed forward to the other qubits, your maybe more precious data qubits, to correct for that noise. So it's basically co-located auxiliary qubits that sense noise and then correct for it. This is actually a really interesting protocol because it helps you to mitigate this kind of global long-range noise where maybe quantum error correction schemes can face challenges, especially at large noise strength. But I'm not saying that you should do this instead of quantum error correction. We will for sure need real quantum error correction. But I'm saying we could actually use the 2 things complementary to each other. And maybe this spectator protocol can help with the global noise. But in order to make this work, what you need is basically mid-circuit readout of these auxiliary qubits. So you have to be able to read out the qubits without decohering the data qubits. You have to do that on a fast time scale so that you still have useful information that tell you something about the data qubits. And then you have to, in real time, perform this feed forward. So obviously, in our case, to implement it, we use the dual species approach. We set aside the cesium atoms as our spectator qubits and the rubidium atoms as our data qubits. And now we have these optical transitions. We also have the microwave transitions to manipulate the qubit states. And simply by dialing in a different frequency, we can choose which one we manipulate. Misha is still answering questions. So which one we manipulate? So here you just see simple Rabi oscillations between the hyperfine states. You can make it slightly more interesting and maybe drive a decoupling sequence here on our rubidium data qubits. And as we make this decoupling sequence, so basically multiple echo pulses, we can get our coherence time of these data qubits. This is here on the order of ½ second. This is not in any way record breaking. This is just for us to establish this baseline and then to see what happens to this coherence time when we also manipulate the spectator qubits, and importantly, when we read them out. So as we read them out, we actually put a lot of laser light on all the atoms. And the question is, does this affect the data qubits coherence time? And this is what we see here now in magenta. This is still the rubidium qubits. And you see that the data, that the coherence time is not affected at all. So this is really great. So we can read out, get information from the spectator qubits without affecting the data qubits at all. And this is, some people like to call this mid-circuit readout. And I should say there are multiple strategies towards achieving this. Dense damper currents group have achieved this by moving a single atom into a cavity readout zone. There are also shelving schemes that maybe make use of more complicated level structures in Mark Safman's group, Adam Kaufman's group, and Manuel Andrews' group, and also from atom computing. Here, the beauty is that we don't have to do anything fancy. Basically, we have done all the work already by having all the lasers double and the trapping double, and now we can just independently read them out without having to do any shelving scheme or movement. So now let's see, can we use this now to correct for this correlated phase noise? So the sequence here is still we are coupling our data qubit, but now we are injecting magnetic field noise. So here in a controlled way, we are injecting noise, but actually the noise is random. At least the phase of the noise is random. So we don't know in each shot what it is. And we actually, if we don't know, it's not just that we have now to rotate a little bit, but actually in each shot, we would have to rotate it by a different random phase to correct for them. So somehow we have to measure this noise. And okay, if we don't know what the noise is, then the coherence is just completely gone. But now involving our spectator qubits, we use the fact that now the spectator qubits also pick up a phase that is correlated with the data qubits, and we can read this phase out. So this is now here in this circuit. In the mid circuit, we read out all the cesium atoms. Then we analyze that picture on our computer. Then we feed forward to this final phase in this decoupling sequence. And as we do that, we can regain coherence. And we could not have done that without doing this feed forward. So here we see that the feed forward corrects for these correlated phase errors. And there are many more details under the hood. We characterize all kinds of frequency and amplitude dependence, but maybe in the interest of time, I will just continue here and just conclude this with this statement that feed forward corrects for these phase errors. So let me move on and now think about, okay, what happens to these Rydberg interactions when we have dual species? Obviously, you can basically think of these dual species as in fact, two independent atom arrays. So if you excite rubidium to the Rydberg states, you get this strong Rydberg interactions for rubidium, or you can excite cesium to the Rydberg state, you get the cesium interactions. This is already nice because you can do it independently. You can decide only rubidium or only cesium. But of course, the interesting case is where you excite both of them to the Rydberg state. And then it really depends on which states you choose. For example, you could choose to excite both atoms to similar principal quantum number Rydberg states. And if you choose to do that, you get similar interaction strengths for the interspecies interaction. So now the interaction here you see for rubidium, cesium, and interspecies is kind of on the same order. And actually, by choosing different states, they can be made more equal, or maybe even the interspecies interactions could be made weaker. But actually, another regime that we are very interested in is actually that is asymmetric in the other direction, where we now pick states where the interspecies interaction is much stronger. So these strong states or strongly interacting pair states, they happen at so-called Förster resonances, where actually this 1/r⁶ dependence that is typical for Rydberg-van der Waals interaction changes into a 1/r⁴ dependence, at least at shorter length scales, and then to 1/r⁶. So it gives you a strongly enhanced interaction. And this is a regime that's interesting because now I could, for example, use one of the cesium atoms to control many rubidium atoms that are not interacting among themselves. Or I could map maybe the state of rubidium atoms onto this central cesium atom and then read it out. And like that, maybe extract something like a stabilizer for an error correcting cone. So I want to show you our progress towards realizing that. And this is now very preliminary data. So don't judge me on the fidelities yet. We are improving all of them. We understand where our infidelities come from. But here I'm just showing you that we can independently drive the cesium ground state Rydberg oscillation. We can independently drive the rubidium ground state Rydberg oscillations. And now if you look at this, what you can do, can basically choose to sit here. You first do pi pulse on the cesium, and then you see what happens to the rubidium Rydberg oscillations, and you see that they are blockaded. There's still a little bit of oscillation left. This is the infidelity we are addressing right now, but clearly you see a large difference between this blue curve and this violet curve, showing you basically for the first time interspecies Rydberg blockade. We are also currently performing a gate with this, but yeah, that I hope to show you very soon. And now in the last 3 minutes or 4 minutes, just want to show you kind of the broader picture where I would like to take this. Of course, in this, in like a single vacuum chamber, you can actually fit quite a number of atoms, maybe in the field of view of a microscope objective. I mean, you can be, I think, quite optimistic that soon we will see thousands of atoms, maybe even 10,000s of atoms. But at some point, you are going to run out of either space in your vacuum chamber or maybe laser power, and you will need, or you might want a way to connect distant arrays. And here's a proposal or kind of a careful analysis of maybe such an architecture by Mark Saffman groups, where he imagines having two actually dual species arrays in these macroscopic cavities and connect them with light. And similarly, a different architecture, but here also already experimental demonstrations by Michel Lukin's group, where I was also involved at that time, where actually we showed that you can combine these tweezers with nanophotonic crystals and actually move these tweezers on and off the crystals. And you could also imagine in such a situation, you have an array that you then can interface with these nanophotonic crystals. Yeah, this is very inspiring to us, and we are continuing down this route now, actually operating at wavelengths, at telecom wavelengths, to really enable long distance entanglement distribution. And our goal actually for this new setup is that we combine all the benefits of atom arrays now with nanophotonics, and not just one device, but actually a whole array. So here you see an array of nanophotonics, and our goal is to combine this array of nanophotonics with an array of tweezers and atoms. And okay, the nanophotonics, they work very well, and they work at the telecom. But more importantly, I'm going to show you now this integration, marrying the two things, the array and the nanophotonics. So this is a separate setup, a different setup. It's actually even smaller than the one I showed you before. So it's very nice and compact. And the special thing in this setup is that we have inside this holding structure that holds this photonic chip. So here we have many nanophotonic crystal cavities on this chip operating at telecom wavelength. This is very interesting because, okay, you could now imagine coupling to multiple nanophotonic crystals at the same time, and then massively enhancing your entanglement rate over distances. And actually the key result, I hope you appreciate, I'm showing you here in the left corner, where I'm showing you a simultaneous image of these nanophotonic crystals with an array of atoms next to it. And actually, in order to do that, we have developed a new background-free imaging technique that allows us to collect this atom fluorescence light, even though many of the lasers, of course, also reflect from these nanophotonics, but we can identify the atom fluorescence without being bothered by any kind of laser reflection. That's very special. That now allows us to carefully move these atoms onto the nanophotonic crystals. And we do see some first indications of coupling, or at least that we are very close proximity to the cavities in this device. So with this, let me conclude. I've shown you first why it might be interesting to go beyond a single species atom array, and I've showed you our dual species atom array in the first small demonstration where we use this independent mid-circuit readout to correct for correlated phase errors. And then I've shown you our preliminary data on dual species interaction. And here the prospect is really exciting, where we now want to combine these interactions with readout. So we could correlate the state of a data qubit with our ancilla atom by first performing a gate and then reading out the ancilla atom without disturbing the data atom unnecessarily. And we have more interesting protocols also towards state preparation of cluster states, and also some ideas on engineered dissipation, where you basically use one species to cause dissipation in interesting ways on the other species. And then I've shown you our second setup, where the goal is really to combine these atom arrays with nanophotonic arrays in order to scale this up and create entanglement over large distances. We are pretty serious about that. We have fibers going all the way from UChicago to Argonne National Lab, so a distance of 20 miles, or actually fiber length is maybe more like 35 miles. But I'm actually very optimistic that we will have some appreciable entanglement rate over such distances. And we also have some projects about coupling atoms to actually other solid state memories in a hybrid approach. So with this, let me thank you very much and thank my wonderful group that has done all this work. Yes, thank you very much.
Thank you so much, Hannes. Seems to be indeed very, very rich system. We have less than a minute for questions. If there is any urgent one, I'm trying to find. Maybe just unmute yourself and proceed.
Can I ask about,
yes.
So how does this background-free technique works? The imaging technique?
Yeah, that's an excellent. Yeah, so the background-free imaging technique, actually, it is very much related to the way we also want to create entanglement. So we want to create entanglement at the telecom wavelength by working between excited states. So we basically have two laser fields that take us to a higher excited state. For example, rubidium would be a 4D state to get here telecom photons out. And now for the imaging, what we do, actually, we leave out the second legs here, and we just go up in a 2-photon process, and then we can detect at a different wavelength than at the wavelengths that we excite with. So basically, this is we currently are doing this for cesium, and we go up on the D2 line and detect on the D1 line. And then basically, I mean, we would be drowned by so much reflections that we're completely blind. But now basically we can filter that completely out and get the arrays. And we even can image on top of the devices with this.
And the atom heating is not a problem.
I think it's yet to be more characterized, but actually, okay, we take a little bit longer for these images. So mainly we are just doing kind of normal kind of polarization gradient cooling. Sometimes we take it on this extra path, and then we detect the photons then. It's cool.
Okay.
Right?
Yes, yes, thank you. Yes.
Thank you again, but we have to proceed because we are quite late. And so the next talk will be given by Christian Coquel from Innsbruck. Tetrasolar group, and I guess we are coming back to chain of ions from 2D neutral atoms lattices, right?
That's right. Yeah.
Okay, good.
Let me just.
Yes, we can see everything is fine. Yes.
All right. Yeah. So thank you very much for the invitation and for giving me the opportunity to speak, and particularly thanks directed to Olga for putting me in this into this very nice session. So I'm going to tell you about maybe one of our most recent projects. I put the archive number here. This is a collaborative work between the theory group of Peter Zoller and the experimental group of Rainer Blatt. And it is about an interesting perspective of looking and analyzing entanglement in quantum simulation experiments. I will show you some experiments from trapped ions, as Olga already said, but it is something that's universally applicable, in particular also to the systems Misha and Hannes were just talking about. So all of you are familiar with this concept of quantum simulation. We have just seen some very nice examples in the previous talks. Usually we have some many-body problem, which we formulate in terms of a Hamiltonian. And in computational physics, the standard approach would be to put this Hamiltonian on a classical computer, and then you can compute properties of this Hamiltonian. But we know that sometimes this is too difficult, and we would rather like to design a special purpose quantum device that mimics the properties of this Hamiltonian in a controllable way. And this idea has now been out there for many years, and we are now in this era of programmable analog quantum simulators. And we have seen very nice examples from Misha and Hannes of Rydberg atoms, but we also have Hubbard models with fermionic atoms in lattices, polar molecules, trapped ions, and we have recently seen also very impressive results with superconducting circuits. And you can now ask the question, I mean, why are these systems interesting? They are interesting because of entanglement. Entanglement is the thing that distinguishes these systems from classical systems. And entanglement is really the topic of my talk. And the situation I will have in mind is a lattice system that is in a pure state. And for the moment, think about this lattice system as being the ground state of a local Hamiltonian. And what I mean by local is this Hamiltonian is a sum of terms hi, and these operator components hi, they might have nearest neighbor interactions or maybe next nearest neighbor interactions, but you can associate them sort of with a single site in the lattice, and this sum I runs over all lattice sites. Now, if we ask about entanglement in such a pure state, what we usually do is we take a bipartition, we split the lattice into a region A and an environment B, and we look at this reduced density matrix of the subsystem A, simply by tracing out everything that does not belong to A. And it is the mixedness of this reduced density matrix that tells us something about entanglement between A and B. Now, what you can always do is you can rewrite this density matrix in the form of a Gibbs state. That's always possible, simply because all eigenvalues of a density matrix are positive, and so are the eigenvalues of such a matrix. And if you do that, you already added a little bit more physics to the problem. You have now a prefactor beta in the exponent, which is an inverse temperature. So the smaller this beta is, the higher the temperature is, and the more mixed your density matrix will be, and the more entanglement there is. But moreover, you also have now a dimensionless Hermitian operator in the exponent. We call this thing the entanglement Hamiltonian. And this is the main subject of this talk. This operator is very interesting for the following reason. It turns out that in a lot of interesting situations, the structure of this entanglement Hamiltonian is very easy. In particular, it consists of the same operators as your system Hamiltonian. These local operators are the same for both of these operators. Now, why is this interesting? Why should we care about this? First of all, if you would know this entanglement Hamiltonian, you have access to a lot of entanglement measures, for instance, to the von Neumann entropy. This entanglement Hamiltonian basically turns out to be the logarithm of the reduced density matrix, and the von Neumann entropy is the expectation value of the logarithm. So it's basically up to an additive constant, the expectation value of this entanglement Hamiltonian. Second, you can do a sample efficient tomography. And this was shown in a very important paper by Anurag Anshu et al. At Harvard, where they showed that if you have a Gibbs state with a local Hamiltonian in the exponent, you can learn it efficiently from a number of samples that scales polynomially with the subsystem size. The third point is that you can test fundamental theories. I will talk about that. It turns out that there are predictions from conformal field theory and relativistic quantum field theory about the structure of this entanglement Hamiltonian. And if you have ways of measuring it, you can check if these theories apply in your quantum simulation experiment. And the fourth point, which I will not talk about today because of time reasons, is if you have the entanglement Hamiltonian, you maybe have ways to probe its spectrum. And this tells you, this you can use to characterize topological phases, because it turns out that there is a one-to-one correspondence between this so-called entanglement spectrum and the spectrum of edge excitations in a topological phase. So far for a motivation, I could now go on, show you just some results from the lab where we measure this entanglement Hamiltonian and how we do it. But before I'm going to do that, I would like to talk a little bit about this local structure. So you can really ask, why should this be the case? Why should the logarithm of the reduced density matrix be such a simple operator? That's kind of a surprising fact or a surprising thing. I will later on show you to which extent this is true. And I would like to motivate this from a quantum statistical mechanics viewpoint, from something that's called the eigenstate thermalization hypothesis. Let's again take such a local Hamiltonian. In a generic case, it turns out, so this eigenstate thermalization hypothesis claims the following. If you sort of diagonalize the Hamiltonian, you look at its spectrum, and you take some eigenstate of this Hamiltonian somewhere from the middle of the spectrum, and you look at local observables from some subsystem A. This eigenstate thermalization hypothesis tells you that local observables, they look like expectation values from a thermal ensemble, as if they are taken in a state e to the minus beta h, where beta is some inverse temperature and h is your system Hamiltonian. Now, if this statement would be true for all observables in the subsystem A, you can actually conclude from that your reduced density matrix takes the form of a Gibbs state, where the Hamiltonian in the exponent is just the system Hamiltonian restricted onto the subsystem. So this is an example where this entanglement Hamiltonian is very easy. It's just the system Hamiltonian itself. It turns out it's not completely true. You have to add some boundary corrections. So at the boundary of the subsystem, there are some deviations. But to a very good approximation, and I will show you in a minute to which extent this is true, you can account for these boundary corrections by introducing a local inverse temperature, not a global inverse temperature, but an individual inverse temperature for each of the Hamiltonian components. What you can do now is you can plot this beta I, this local temperature profile over the subsystem, and it will somehow look like this. It will be constant in the bulk of the subsystem, and towards the boundary, it usually drops off. These are these boundary effects I was talking about. And what's interesting is that in this eigenstate thermalization argument, at no point it appears that this temperature, that the height of this temperature profile depends on the size of the subsystem. It really doesn't. So if you make the subsystem a little bit larger, it will look like this, and a little bit larger, it will look like that, and so on. But the height is constant as a function of the subsystem size. And what you can conclude from that, if you remember now that the von Neumann entropy was basically the expectation value of this entanglement Hamiltonian, it means that in this one-dimensional scenario that I have drawn here, your von Neumann entropy will scale linearly with the subsystem size. It will, in general, scale with the volume of the subsystem. It is a volume, you have volume law entanglement in such highly excited states. Now you can ask what happens if you go to the ground state. And this has been investigated by people working in conformal field theory. It turns out that if you have a conformal field theory, if your state is invariant under conformal transformations for a lattice system, this basically means that you're sitting at a critical point. You can more or less analytically derive how this temperature profile looks like. And what these people derive here is that it takes the form of a parabola. And now there is suddenly a dependence on this temperature profile on the subsystem size. If you make your subsystem larger and larger, these parabolas will grow. And there is a very easy or a very nice intuition behind this. If you remember that this is some local inverse temperature, what this tells you is that your subsystem close to the boundary where it touches the environment, it is very hot, and in the interior, it is very cold. So all that it means is that most of the entanglement your subsystem A has with the environment A bar comes from particles that sit at the boundary of the subsystem. So that's actually pretty intuitive. And if you plot here the von Neumann entropy as a function of the subsystem size, you will have an area law. And because we're sitting at a critical point, there will be a logarithmic correction to this area law. So this is at the critical point. Now you can ask the question, what happens if you move away from the critical point? This has been investigated in a paper from Victor Eisler, where they study this in the context of free fermion models. And what they find is that these parabolas, they change into something that that looks like more like a triangle. So this profiles change into triangles. And this transition from these parabolas to the triangles, this seems to remove the logarithmic correction from the von Neumann entropy. Okay, up to this point, I just told you a nice story. I was drawing some pictures. Let's check if this is actually true in practice. Let's do some numerics. What I did here is I just took an XXC model, a Heisenberg model in 1D for 51 sites. You will see in a minute why 51 sites, because this is the number of ions our ion trappers have in the trap at the moment. And this model has a very simple phase diagram. So as a function of this anisotropy parameter, if delta is smaller than -1, it's a ferromagnet. If it's larger than 1, it's an antiferromagnet. And between delta -1 and 1, the model is described by a CFT, by a conformal field theory with central charge equal to 1. And I was not looking at this point, at this isotropic point, delta equal 1, was computing eigenstates of this thing. And you can now look at this entanglement Hamiltonian. There are many methods which explain how you can extract this entanglement Hamiltonian from your state. I'm not going to explain how they work, but they are very easy to apply. You can program them in about 7 lines of code. And if you do this numerics here, this is what you get. So you really see that in the ground state, you see beautifully these parabolas. You see a von Neumann entropy that looks like it scales logarithmically with the subsystem size. And here I did it for the 100th excited state. And there you see that the height of this temperature profile is constant over the size of the subsystem. And you see that the von Neumann entropy scales linearly with the subsystem size. Now let's move to the lab. This was just some numerics now. Let's see if we can see the same thing in experiments. What we do in these experiments, we prepare approximate ground states of this XXC model with a variational approach. So we have a quantum circuit. We can execute certain types of gates. This machine is a programmable analog quantum simulator. So what these experimentalists can do is they can execute a global gate that acts on all the ions, which basically is time evolution with a long-range Ising Hamiltonian. They can realize that by shooting a bichromatic laser beam on this ion chain and adiabatically coupling it to phonon modes. And another thing that they can do are single qubit rotations. And what we do is we optimize this circuit in a feedback loop with a classical computer. We optimize the energy of this Heisenberg Hamiltonian, we minimize it, and eventually this allows us to prepare approximations to the ground state of this Hamiltonian. And after we prepare the ground state, we can analyze the state. So we draw some measurement data from this state, and then we have ways of learning the entanglement Hamiltonian. I'm not going to explain how they work. They are written up in this paper. It's not very difficult. It's basically a fitting procedure. And we did this for 2 different parameter regimes of this Hamiltonian, for delta equal 1, where the state is supposed to be critical, and for delta 1.7 in the antiferromagnetic phase. This is the von Neumann entropy as a function of the subsystem size. These are really experimental data now here, these blue squares. It just looks very boring. It's basically an area law. But we can also now look at this entanglement Hamiltonian. And what we see is that at this isotropic point, we really see beautifully parabolas. And as we move into this antiferromagnetic phase, we see indications of what has been seen before in numerical simulations, that this temperature profile changes into something which is more like a triangle. So we see indications of that in the experiment. In the next step, we also wanted to see, can we sort of confirm these predictions from the eigenstate thermalization hypothesis? So can we also look at highly excited states in this model? And what we did is we added just an additional quench in the beginning, which sort of scrambles the initial state. And the effect of this is that it kind of heats up your system. So this prepares for us a superposition of states somewhere in the middle of the spectrum. And when we look at the situation there, we really see now that the von Neumann entropy scales linearly in the subsystem size. So it looks like that we have a volume law. And also in the entanglement, in this temperature profile of the entanglement Hamiltonian, we see that that it develops a plateau that is flat, and it is actually constant as a function of the system size. All right, so this is basically all I wanted to say. I'm now at the conclusions. So I hope that in this very, very short talk, I was somehow able to convince you that that this entanglement Hamiltonian is pretty interesting, that this is an interesting and also useful way of analyzing entanglement in these quantum many-body states. I was only talking about one-dimensional systems, but we have indications that these things also work in higher dimensions. So I think this would be very interesting for this type of Rydberg experiments where you have atom arrays that you can arrange in two-dimensional and maybe even three-dimensional geometries. And maybe one thing, this is something I just want to mention very, very briefly. Please don't nail me on this. We recently started to look into this. There seemed to be some relation to gravity, actually. So some of you might have heard about this correspondence between conformal field theory and anti-de Sitter space. Anti-de Sitter space is basically a model of space-time on which gravitational theories are defined. And this correspondence between this ADS and the CFT basically says that there is a dictionary that you can use to translate correlation functions in one theory to correlation functions in the other theory. And one of the very interesting outcomes of this correspondence is this Ryo-Takanayagi conjecture, which basically says if you want to know the von Neumann entropy of a subsystem in this CFT, what you have to do is you draw this minimal surface into this anti-de Sitter space, and the von Neumann entropy is basically given by the area of this minimal surface divided by 4 times the gravitational constant. So there are some connections to gravity. And what we did in this experiment, I was just telling you about, so we tried to provide some experimental tools to study this conformal field theory in the lab. We basically study this profile of this entanglement Hamiltonian, not only for connected, but also for disconnected subsystems, actually. And the next natural step would be not only to study this conformal field theory on the surface, but also probe into the bulk, into this anti-de Sitter space. Basically, there are papers that sort of say that this anti-de Sitter space is kind of related to special tensor networks, to mirror tensor networks, actually. And what we are trying to do now is to establish some tools that you can actually learn the underlying tensor network structure of these states from local measurements on your quantum system. So I think that this is some exciting future direction. And this is basically my conclusion. With this, I'm at the end, and I thank you very much for your attention.
Thank you so much, Christian. Because it's exactly 20 minutes, maybe just one short question. If somebody has urgent question. Vitaly, if it's short again.
It's a very general, simple question. When you are dealing with quantum simulations and measurements in this system, you have to measure bare atoms, not the quasi-particles or eigenstates of Hamiltonian, and then you immediately come to the problem of squeezing. Why you never mention squeezing in this system? The squeezing and entanglement are responsible for the quantum supremacy, in a sense, of many-body quantum system. What is about squeezing in your system?
I'm not sure I 100% understood your relation to squeezing and quantum supremacy. That you squeezing. Squeezing
of course, the atoms they are in the squeeze states. Obviously, all bare atoms, contrary to the eigenstates of the Hamiltonian. And then when you measure the system, you discuss mostly kind of global characteristics like in von Neumann entropy or something like that. But in the measurements, you have to deal with the bare atom states, which are squeeze states.
I think I would have to understand a bit more deeply what you mean by that. I mean, what we do, the kind of measurements that we do in this experiment are basically quantum projective measurements in some local basis, right? So, I mean, we do basically something that we call Pauli measurements. So our experimentalists, they have control over the individual atoms, over the individual ions, and you can basically arbitrarily rotate them on the Bloch sphere. What we do with these experiments, we prepare some entangled many-body state, and after that, we sort of perform quantum projective measurements where we sort of can individually each atom individually measure in its own separate basis.
I'm afraid we have to stop. Maybe you can communicate by chat or whatever.
You can maybe in the chat.
We have to proceed.
Sort
I'm sorry. I'm very sorry, but we are late. And so thank you again, Christian. And the next talk will be given by Shimon Kalkoitz from University of Wisconsin-Madison and Department of Physics, University of Berkeley. And now we are moving to the optical clocks, but essentially with the same type of systems.
Yeah, thank you very much, Olga. So hopefully you can see my screen and my mouse.
Yes, we can.
Great. You can hear me, it sounds like, too. So perfect. So first of all, thank you to the organizers, and thank you especially to Olga for the invitation to give a talk in this very exciting session and in this very exciting workshop. I have to say that it is a bit of a change of subject, a little bit, but there are some nice connections, actually, especially to some of the things that both Misha and Hannes talked about in their talks. As you'll see, part of the goal of my group is to apply some of the same techniques and tools that are being used in quantum simulation and quantum computing now to metrology and precision measurement, and especially to optical atomic clocks. The other thing I want to mention actually is that I'm actually changing institutions. So as I'm listening to all the talks this week, I'll actually be packing up my office, which is quite sad for me, but I'm moving from the University of Wisconsin, where I've had a really great experience and I'm very sad to leave, to UC Berkeley. And I am looking for new students and postdocs and things to join me there at Berkeley. So, okay. So I think my guess is most of you are familiar with atomic clocks, but because this session was primarily focused on quantum simulation, I want to start by giving a very quick reminder of how atomic clocks actually work. So a clock is just something that has a specific frequency that we can count in order to keep track of time. And that's what's known as the local oscillator. And then it's a counter that actually counts the oscillations of that local oscillator. And these two components are really what make a clock. But of course, the issue is that any simple harmonic oscillator that we can come up with, like the quartz tuning forks that are in our laptops or in our cell phones and all of our modern electronics and things like that, or a pendulum, any of these things will be man-made. They'll be imperfect. They'll be different from each other, and they'll also drift over time as the environment changes, as things like the temperature changes or as a piece of dust settles on top of this tuning fork. And so what makes an atomic clock is we take the frequency of one of these local oscillators and we compare it to a well-defined transition. Here I'm showing this classic 21 centimeter line of hydrogen, this hyperfine transition for hydrogen, and we can use the information that we get back from determining whether or not the local oscillator is basically on resonance with this atomic transition to feed back and correct for the imperfections in each of these local oscillators, the fact that each one is slightly different, and also for the sort of environmental changes and the instabilities in these local oscillators that result from that. And that's what makes an atomic clock. And of course, these have been really transformative quantum technologies. I think you could make a strong case that in terms of their impact on our everyday lives, there's maybe nothing that impacts our everyday lives, that's truly a quantum technology as much as possibly the GPS network. Normally, I would say that helped us all get to the conference, but of course, today we're all in our respective institutions. But nevertheless, the GPS network is really transformative. And also, of course, we've gotten so good at making these clocks that now we can measure these hyperfine transitions of cesium and rubidium better than we can measure anything else with units. And so we've now adopted a new system of units, the new SI, where every other thing with units is defined with respect to the hyperfine transition of cesium, because clocks are really the best measurement devices that we can make. And so what that means is that also, if we want to measure anything with units better than we currently can, that on some level requires also improving clocks. And that motivates making better clocks. And there's been a real kind of boost in performance of clocks over the last couple of decades that has come from looking at this expression for the quantum projection noise of a clock. Basically, every time we compare our local oscillator to our atomic transition, we have to measure our atoms at the end, and we measure them whether they're either in the up or down state of this clock transition. Here, this hyperfine, the two hyperfine states of hydrogen. And when we do that, we project the atom into one of these two states, and there's a certain noise associated with that. We can't measure each atom being half and half. Instead, of course, we only ever measure each atom either in being up or down. So there's a kind of quantum coin flip that happens. We can very easily from that write down an expression for how good our atomic clock can really be. And when you look at this expression, you see right away that there's this nu naught, this frequency of the transition or frequency of the local oscillator that we're comparing to the transition in the denominator. And we can see that just by increasing this, we improve the performance of our clock. This is quite intuitive. All it's really saying is everything else being equal, if we are counting a local oscillator that's ticking faster, we'll make a better clock because we can just determine that there were more ticks per unit time per second, for example. And so that has motivated the move from microwave frequency clocks like the hydrogen maser that takes advantage of this transition, or the rubidium or cesium hyperfine transitions, to optical transitions in clocks. And that gives you in principle something like between 10 to the 5 and 10 to the 6 improvement if everything else is equal. The atom that we use in my lab, and one of the atoms of choice for these optical clocks is strontium 87, which has this beautiful optical transition that still has sort of line widths, maybe not quite as narrow as the hyperfine transitions of rubidium or cesium, but really still quite narrow for an optical transition, 1 millihertz or possibly even slightly less, on an optical transition that's 400 terahertz, which gives you a quality factor of 10 to the 18 that we can take advantage of to make a really good clock. And this is what we use in my lab. And there's a number of other groups and standards institutes around the world that are using this element. And so taking advantage of these new technology of optical clocks to keep track of time, we've seen this amazing improvement by several orders of magnitude over microwave clocks. And we're now at this remarkable level of 10 to the minus 18 performance, meaning that if you kept two of these clocks ticking side by side for 10 to the 18 seconds, which corresponds to longer than the age of the universe, longer than 14 billion years, those two clocks would still agree with each other on the age of the universe to better than 1 second, which is really, truly remarkable. And it opens the door to all kinds of new and somewhat more exotic applications of these clocks, going beyond GPS and unit definitions. Now we can start to use these clocks for things like measuring Earth's gravity using relativistic time dilation, or searching for variation in fundamental constants in order to try to maybe detect dark matter, or even possibly one day to use these clocks in space to detect gravitational waves. And this is really what I would say all of my research is in my group is focused on these clock experiments, is developing and testing out some of these new applications and really pushing on them. And when you look at a lot of these applications, you realize that as good as these clocks get, perhaps not surprisingly, these emerging applications, we're still just at the level where we're starting to be able to do interesting things. So for example, if you want to use these clocks to measure Earth's gravity, these clocks are just entering the regime where they can measure things that no other measurement tools can. And if you want to use these clocks to measure gravitational waves in space, we actually still need to improve their performance by several orders of magnitude in order to have a hope of really detecting gravitational waves and being competitive with other ways of doing that. And so that really motivates my research. So to that end, we've built a strontium optical clock. As I said, in Wisconsin, this apparatus is now moving with me to UC Berkeley. We'll also be building a second clock in Berkeley. So we have this really nice vacuum chamber. We've achieved very good vacuum here. We have strontium 87 atoms trapped in an optical lattice here. And we've purchased a very nice local oscillator for this optical transition. This is a 1 hertz or so line width commercial clock laser system that we bought from Menlo. And it's this 12 centimeter ULE cavity that we lock our laser to. And then we probe this 1 millihertz line width transition with this about 1 hertz line width laser or so. And when we do that, we end up, of course, being limited not by the atoms, but by the laser itself. So we find that when we do multiple, Ramsey experiments and compare the results, what starts to happen if you interrogate for longer and longer is that the phase of the second pi/2 pulse starts to drift. And so that's what you want to correct for. That's the whole point of making the clock in the first place. But what that means is you can't interrogate for too long before you start to lose contrast in your Ramsey fringes. And so we're limited to a T2 star time, to a coherence time of about 100 milliseconds or so. And that limits the performance of our clock. We can go back to this QPN expression I already showed you, and we can just plug in the numbers here, and we would naively get a stability of the clock of 4 times 10⁻16 per root hertz. So as we average down, we can measure, better and better, with better and better resolution. But at 1 second, we would be sensitive at about 4 parts in 10⁻16 or so, which is quite good for a clock. This is really pretty impressive. But then we go and measure in our lab what we actually get, and we find that we're quite a bit worse than that, more than an order of magnitude worse than that. And the reason for that is that naive expression, that QPN expression, only accounts for quantum projection noise. It doesn't account for another form of noise, which is called Dicke noise. And this is basically the fact that our clock, we have dead time. We're not always comparing our local oscillator to our atoms. There's time when we're reloading our atoms into the lattice and things like that. And we can't keep track of what the local oscillator is doing during that dead time. And then you end up aliasing a bunch of the higher frequency clock laser noise, the noise on the laser, into your measurement at the end. And this noise that you get from this process swamps our quantum projection noise. So instead of having this kind of nice, clean, very intuitive expression, we have this quite messy, I have to say, and frustrating expression. We can sort of simplify this a little bit, and we get something that looks like this. So basically, the Dicke noise for one of these clocks scales as the noise on the local oscillator itself, the instability of the local oscillator, and then it still scales as you expect with things like square root of the interrogation time and square root of the total measurement time, but it doesn't anymore do things like scaling with atom number. And this is quite unfortunate because it means if we add more atoms to our clock, we don't get a better performance. It also means if we try to do things like use quantum enhanced clocks using spin squeeze states and things like that, we really can't benefit from that anymore. And it means that our clock is just doing much worse than we naively expected. And to give you some sense, if we're going to try to reach down to this 10⁻20 level to say measure gravitational waves or something, at the stability that we're achieving in my lab right now, it would take 44,000 years to average down to 1 times 10⁻20 to measure just one data point. And of course, that is not a reasonable kind of measurement to make. And so we have to look at ways that we can improve that performance, and we can look at this expression. And what's frustrating about this expression is there's really not very many things that you can do to improve it. One of the things you can do, of course, is to try to make a better local oscillator. And I have to say that my postdoc advisor, Jun Yi, who is one of the plenary speakers who will be speaking tomorrow in this workshop, has done pioneering work on making better and better lasers, better clock lasers with lower and lower noise to reduce this. And that has allowed him to achieve really remarkable clock performance of 5 times 10⁻17 per square root hertz. And that's one approach. But of course, A, for a given local oscillator, even for this local oscillator, you'd like to do as well as you possibly can. B, these kinds of lasers, this single crystal silicon cavity system that June has developed, there's only 2 of them in the world right now. We don't have, I don't have access to them in my lab. And in addition to that, these aren't really very portable systems, and it would be very hard to send a system like this into space, for example, to do gravitational wave detection or something like that, or to take it around in a truck to make measurements of Earth's gravity. So we need other solutions. And so the question is there anything we can do in my lab to improve the performance, given that we're using this kind of commercial, fairly portable, rack-mounted clock laser system? And the answer is yes. And for the rest of my talk, I want to tell you about 2 different approaches that we're taking that we've developed in my group to using the fact that we can actually load multiple ensembles in kind of a similar way to the kinds of experiments that Hannes and Misha were telling you about with atom tweezers. We've developed what we call a multi-ensemble or multiplexed optical lattice clock. And I'll tell you about 2 different techniques that we have to use that to actually enhance the performance of our clock. So first, I want to focus on a technique where we use these multiple ensembles to do a sort of more sophisticated version of phase estimation in order to actually increase our coherent interrogation time given our local oscillator and make a better absolute clock. And then in the second half of our of the talk, of the remaining time, I'll tell you about the different kind of approach where we use differential comparisons between the clocks to actually completely cancel out laser noise and to learn about the difference between 2 or more of these clocks without worrying about the local oscillator anymore and actually getting back to this beautiful QPN limit that we'd like to be sitting at. So as I said, here's our apparatus. And then what we're doing that's different is we're actually loading multiple regions of the same optical lattice with spatially resolved clouds of strontium atoms. And this is what this actually looks like in our experiments. These are camera images from our experiment. You can see we've loaded one region here. We shift it over. We turn our standing wave into a running wave optical lattice, move over, load a new region from the MOT. Just then we turn the MOT off and drop some of the remaining atoms we hadn't trapped. And now we're left with two ensembles that we can resolve with our camera and read out independently. Each of these ensembles have roughly a few thousand strontium atoms when all is said and done. And now we basically have two clocks that we can use to try to improve the performance of our clock over the traditional technique where you just have one ensemble of atoms that you probe, with one clock laser. So why does that help? Well, if you look at this expression, one of the only things that you can do to really improve the performance here is increase your coherent interrogation time. And you could say, well, if you look at the numbers I've plotted here, I only have a 20 millisecond interrogation. If I just doubled this number, I could reach a stability, or maybe made it 4 times as big, I should say. I could reach a stability that's more like this, and that would still look like it's within your coherent interrogation time. So why did I stop at 20 milliseconds? And the answer is we actually can't really, even though that's the coherence time when you average over many experiments, if you're actually trying to run your clock, you need to lock your clock to the your local oscillator to the clock transition. And so you need to stay locked to it and keep track of the transition as it drifts around. That's what we're doing here. And here we're running 2 interleaved clocks. So we're basically 2 independent versions of the same experiment where we're locking our clock laser to our atoms and we just interleave them. And you can see that they track each other very nicely. And then at a certain point, one jumps with respect to the other. And we plot the difference between these two locks. You can see that you have this big jump in frequency. And what this corresponds to is what's called a phase slip or a fringe slip. Basically, if your local oscillator ever drifted by enough so that you end up over the hump of your Ramsey fringe here, you can't tell that happened. You get confused between measuring this excitation fraction and this excitation fraction. Those are the same, but they correspond to 2 different phases or 2 different detunings of your clock laser. And so what that means is you need to restrict yourself to interrogation times where you never accumulate a phase of more than plus or minus pi over 2. And that's what keeps us at this 20 milliseconds. If we go to 40 milliseconds, as I'm showing you here, we every once in a while will get one of these fringe slips, and that will completely throw off the stability of our clock. As you can see, it doesn't even average down anymore with averaging time. And so, so why do 2 ensembles help? Well, if you have 2 ensembles, you can make them 90 degrees out of phase with respect to each other. And when we do this, we can plot the outcomes of the experiments parametrically, but there's different ways to think about this. We call this quadrature Ramsey spectroscopy. Basically, now we can disambiguate the outcome of this experiment, because when you have these 2 out of phase Ramsey fringes, now if you accumulated this phase, you'd measure these 2 excitation fractions, which would be sitting here on this circle when we plot these experiments parametrically. But when we accumulate this phase, as I'm showing you here, then in fact you measure this excitation fraction for the 2 regions. And so what this allows us to do is to take full advantage of the full minus pi to pi extent of the Ramsey fringe and double our coherent interrogation time for the same laser. The way we actually achieve this 90-degree phase shift is by applying a magnetic field gradient and loading 2 regions that are spatially separated. And we tune our gradient so that for a given interrogation time, our 2 clouds end up 90 degrees out of phase. And then we use this quadrature Ramsey as a more sophisticated phase estimator. And you can see that actually allows us to double our interrogation time before we start to get phase slips. So when we do the standard Ramsey, which is SR here, after about 20 milliseconds or so, we don't know exactly where we start to experience fringe slips or phase slips. But when we use this quadrature Ramsey technique, we can go all the way out to 50 milliseconds before we start to experience these fringe slips. And that then allows us to actually achieve a better absolute stability of our clock compared to a single ensemble case. Of course, we'd like to do more than that, and we don't have to stop at loading just 2 regions. Here's a video where we load 6 regions of our lattice. And so we'd like to say, well, can we push this beyond just going from pi over 2 to pi? Can we go beyond that? And the answer is yes, but it's more challenging because now it's not sufficient to do the same interrogation for both clouds and just to have them 90 degrees out of phase. We actually need to be able to apply different sequences to each of the different clouds. This kind of connects to some of the techniques that both Misha and Hannes were talking about in their tweezers, where we'd like to somehow have independent control over these ensembles, but still only globally address them. And for example, Hannes achieves this by actually using 2 completely different species of atoms, cesium and rubidium, in order to get independent control. Misha does this by moving his ensembles around into different regions. we are going to use a slightly different technique that we've developed to do this with only strontium-87 and without moving them, because we don't have independent control over these ensembles. They're all in the same optical lattice once we've loaded them like this in a chain. So what we do instead is we still take advantage of this magnetic field gradient, and we take advantage of the hyperfine structure of strontium-87, which has in the ground state, you have F equals 9/2. So you actually have 10 of these different spin states here. And what we can do is, using clock pulses, we take all four. Here you can see we've loaded 4 different regions. We take all 4 of these regions. We first put them up here with a pi pulse. Then we do a pi/2 pulse. So now they're in a superposition. But then we do another pi pulse, so that actually we're in a superposition of 2 different nuclear spin states in the same clock state. And then we allow this state to precess for some amount of time in this magnetic field gradient. And we pick that time very specifically so that when all is said and done, they've accumulated different amounts of phase, because they're at different locations, spatial locations in this field gradient. And we do it such that 2 of them accumulate an even integer of pi phase, and 2 of them accumulate an odd integer of pi phase. And so that means that when we close our interferometer, we're left with 2 of these ensembles that are in the excited clock state, and 2 of these ensembles that are in the ground clock state. And these 2 states now have different transitions, different clock transitions out of them, that allow us to independently control these different regions. And you can see that here. So for example, this is much like some of the crosstalk plots that Hannes and Misha showed. You can drive one of these transitions, and we'd see 2 of our ensembles oscillating, experiencing Rabi oscillations, and 2 of them that don't really experience any oscillations, and vice versa when we drive one of these other transitions. And this now allows us to do a more sophisticated version of a phase estimation algorithm with 4 ensembles, where we can now push beyond this 50 millisecond interrogation time that we got with quadrature Ramsey spectroscopy out to 85 milliseconds with a combination of this more sophisticated phase estimation and quadrature Ramsey. And you can see that in the end, for everything else being equal, so for the same amount of atoms, the same everything, same dead time, we actually double the performance of our clock. We reduce the instability of our clock by a factor of 2 using this combination of tricks. And I think this is a really promising technique. So just to kind of highlight that, we can go out here at this 85 millisecond point, which is the furthest that we were able to push this with 4 ensembles. And we can look at just one of the ensembles and look at the phase that you accumulated in Ramsey. And you can see that actually, if you just did the naive Ramsey interrogation, standard Ramsey, then you really get a flat distribution here, because your phase is essentially completely random from -pi/2 to pi/2. But if you use this quadrature Ramsey technique, you can now decode from -pi to pi, and then you start to see a little bit more of the kind of distribution that you would expect. And then if you use that combined with the phase estimation algorithm, and using the fact that you have information from the other ensembles that you interrogated for a different amount of time, you can really recover the full distribution here. And what this is showing you is each of these events here that occurred would have been a phase slip for a standard Ramsey technique. But now with this 4 ensemble technique, none of them are phase slips anymore. We're actually correctly disambiguating or recovering the actual phase that was accumulated, or the detuning of the local oscillator. You can, of course, ask, well, how far can you push this, and how does this scale as you continue to add more ensembles? And there's this beautiful paper that's really only on the archive from 2013 from Rosenband and Leibrand, where they actually thought about this, and they pointed out that if you use sort of much more sophisticated things that we can't do yet, where you actually can reuse the ensembles without reloading the atoms each time, and you can also make mid-circuit measurements, meaning that you can measure one set of ensembles while the other ensembles are still being interrogated. You should actually expect to get exponential scaling of your clock performance with atom number. This is not something we can achieve yet, because once we've done a measurement, once we've done a Ramsey sequence, we just store our atoms until the end and we read them all out at the end. This would require being able to read them out in the middle, which requires mid-circuit measurement. And that's the kind of thing that's now being done, as we heard about in Hannes's very nice talk, in some of these tweezer experiments. And so I think it's actually very promising to think about, continuing to combine some of these techniques from these tweezer experiments that we heard about from Misha and Hannes with some of these clock techniques in order to keep pushing the performance. Okay, so now I know I'm running out of time, and I want to quickly just say that still, we've now improved our performance of our clock by a factor of 2 in terms of the stability. This is still not really viable. We're now trying to get to 10 to the minus 20, and that would take 11,000 years to average down, so still not looking very good. But in the remaining couple of minutes, I just want to quickly tell you about some results that we had before we had these results, where instead we use differential comparisons between these clocks. And so the idea here is we're probing our ensembles with the same clock laser, so we can just probe way beyond the coherence time. Here we go out for 8 seconds, and you can see the outcome is completely random, but we have 2 ensembles, and if we look at the outcomes of the 2 ensembles, they're actually highly correlated. We can again plot them parametrically like we did before when they were 90 degrees out of phase, and we now see that every single outcome of every single experiment lies on an ellipse, and this ellipse is actually telling us about the frequency differences between these 2 clocks. So by fitting to this ellipse, we can now actually still learn about the frequency difference between these 2 clocks without caring about what the clock laser is doing at all. And this allows us to go out to much, much longer coherence times. We go from 100 milliseconds and then 85 milliseconds using the trick I told you before to now 26 seconds. And that gives us this remarkable stability. We achieve stabilities below 10 to the minus 17 per root hertz, and we're able to average down to the 10 to the minus, into the 10 to the minus 20s, the high 10 to the minus 20s. I want to mention again that June Yi's group also did similar experiments, looking at multiple, sort of splitting one spatially extended cloud into different regions and doing a comparison between those regions, and achieved even better performance. But that was still with this beautiful world's best clock laser. And so I think it's quite promising that we achieve some of the same performance using a commercial laser that's orders of magnitude worse. So I'm going to sort of stop there, but just say that now with this differential technique, we can, reach a stability of 10 to the minus 20 or average down to 10 to the minus 20 in only 6 days instead of 11,000 years. And this is very promising for a whole range of different applications, including things like tests of relativity. We were able to measure the gravitational redshift in our lab from millimeter differences in height between these clocks using this technique. And I think it's very promising going forwards. And so with that, I just want to thank everybody in my group who did this work, all the funding agencies that supported it. And thank you for your attention. And I'll just take questions if there's any time left.
Thank you so much, Shimon. Very interesting results. And
thank you.
If there are questions, maybe I'll ask the first question. I'm afraid I missed the main point. Why the increase of number of atoms simply doesn't help you somehow to increase the stability?
Great. So it depends what you're limited by. If you're actually quantum projection noise limited, then increasing the number of atoms does help. And actually, one of the nice things about this technique where we do these differential comparisons is you can see that we're actually achieving the quantum projection noise limit. That's the red dashed line here. However, for almost all standard optical clocks, you don't achieve the quantum projection noise limit if you're doing the standard technique, because you're limited not by the noise of the atoms, but the noise of the laser. This is what's known as the stick effect. And so the issue is that there's different ways to understand it, but the issue is basically that we're not always measuring what the local oscillator is doing. There's dead time where we have to reload our atoms. And anytime you have dead time, you end up aliasing this high frequency laser noise. You can't tell the difference between high frequency noise and low frequency noise anymore. And so you end up aliasing down a lot of this high frequency noise, and that swamps your quantum projection noise. So you just have more noise from the local oscillator than you do from the atoms, and you don't benefit from more atoms anymore.
I see. Thank you. And so that once again, so how the scaling would work with increase of the number of ensembles?
Oh, yeah, right. So that's a very interesting question. So as I said, it's been shown that with some additional tools that we don't have yet, like being able to do mid-circuit measurement of one ensemble while still interrogating another ensemble, then I think you can get this exponential scaling. I would say it's an open question how well you can do without having things like that mid-circuit measurement. But actually, I believe we can still achieve exponential scaling with atom number, but with a hit of a constant factor, basically. So we can't do as well as that Librand and Rosenband paper that I was showing you indicated, but we believe we haven't proven this, and I think it's actually really an open question. We believe we can still get something like an exponential scaling with a number of ensembles, which then also kind of corresponds to an exponential scaling with a number of atoms. Using the kind of techniques that we're using, it just gets increasingly more complicated the way that we're currently doing it to achieve that. We're working on demonstrating that, and I think we can do it. But so far, we've only demonstrated up to 4, so it's hard to claim any kind of scaling. But right now, we increased the number of ensembles by 4, and we improved the stability by a factor of 2. You can read into that however you'd like, I guess.
Thank you very much. If there is one more urgent question. If not, let's thank all the speakers of our session again, and we meet for the next session just in about 10 minutes. Thank you.
Thank you very much.
Thank you, Shimon.